My name is Terrence Barkin. I'm the Executive Director of the Graphene Council, and we're hosting today's session on Graphene Hall Effect Sensors used in extreme environments. And we're extremely pleased to have Rosie Baines from Paragraf presenting today's topic. And so with that, Rosie, I'll turn it over to you. It's all yours. Thank you.
Thanks very much, Terrence. So I'm Rosie. I'm a scientist at Paragraf, and it's great to be able to talk to the graphene community about some results that we've had with our Graphene Hall Effect Sensors in extreme environments. So just briefly, I'll touch on who we are here at Paragraf. So we started off as a spin-out company from the University of Cambridge, and our founders developed the mass production of large area graphene, and that's kind of the basis on which the company was founded. So that was in 2017. I actually joined the company in 2018, not long into its life. And we've had several exciting moments, such as the shipping of our first graphene-based sensor in 2019. Now we're a growing global presence based mostly here at our facility near Cambridge, where we've got many different capabilities, including our clean rooms, biosensor labs, and a growing staff with many different areas of expertise. So a very exciting place to be. And of course, what makes it so special is our unique graphene manufacturing process. So we have a direct to wafer transfer-free process that produces contamination-free graphene. So this is across a whole wafer, such as the one shown here. And all our processes are standard semiconductor manufacturing chain compatible. So it's a very, very scalable, very kind of directly applicable process to standard manufacturing chains, and we can apply this to a variety of different graphene-based structures. So taking the graphene that we've fabricated all the way through to usable end products. So the one that I'll be talking about today is our magnetic sensor, so our Hall effect sensor. So this operates on the basis of the Hall effect, which is explained in this graphic here. So the active material, which is shown by this red cross shape, so that would be the graphene with a current flowing across one direction here. And when that's in the magnetic field, there's a deflection of the current, and this is measured as a voltage in the perpendicular direction. So this is the graphene responding to the magnetic field with a measurable response, and the magnitude of that tells us information about the field strength. So there are a variety of different applications for this, some of which I've highlighted here in the images. So big markets such as automotive, all the way through to medical and more kind of high-level research-based applications as well. So graphene's perfect for this due to its electrical properties. So it's things like its high sensitivity, general robustness as well, make it very suitable as a sensor. And this is really useful in extreme environments where conventional sensors are somewhat limited. So one such environment is at cryogenic temperatures. So with cryo-capable sensing, we can have accurate measurements of magnetic fields all the way from nanotesla to tens of Tesla. And this would be operating at less than 10 Kelvin. So that's the kind of conditions that we'd be talking about for these measurements. So this would allow measurements in a huge range of fields, including these more research-based ones that are highlighted here, all the way through to more kind of commercial ones, such as medical or even space-based applications. So few conventional Hall sensors really operate well under these conditions. And in fact, no conventional Hall sensors are rated to millikelvin temperatures, bringing in the high magnetic fields as well. So other sensing techniques might be able to operate like this, but usually only in narrow field ranges, which means that more than one sensor would be required per measurement. So it doesn't kind of flow quite as nicely as measuring with just one sensor over the whole range. Also, at cryogenic temperatures, the quantum Hall effect comes into play. So this is just explained very briefly. Here we have on the left side the classical Hall response. So we have Hall resistivity increasing linearly with magnetic field. Whereas at cryogenic temperatures, we start to see the quantum Hall effect come into play, where we come out of this kind of linear regime and we instead see the resistivity increasing in fixed plateaus. So that's something that becomes relevant for some of the data that we have later on. So we have tested our graphene Hall effect sensor under a kind of like a range of these conditions. And just some of the immediate things that spring out of it are just generally looking at the robustness of the sensor. So you can see from these images here, here's our sensor kind of mounted on the end of a probe, just there in its package and just exposed to these extreme conditions. So we saw robustness to thermal shock during cycling between 4 Kelvin and 300 Kelvin, as well as very low temperature operation, so working at millikelvin temperatures, and that's something I'll come on to in the next few slides as well. Looking at electrical conditions as well, so we tested up to 200 volts, and it again showed good robustness and minimal change in performance. Also, it operates at very low power, so we're looking at picowatts to milliwatts, which is obviously ideal for cryogenic applications where minimal heat generation is desirable. But there's also scope to operate at higher currents if that's something that's necessary for the application as well. So talking a little bit more in detail about the electrical properties. So this is something that we have a very good control over for the graphene itself. So by kind of going through that fabrication process, altering growth and processing conditions, we can have control over the carrier concentration of the graphene. And the reason for this is that we might want to maximize certain properties that allow us to operate under certain ranges of conditions. So for example, with a low carrier concentration, this results in a high sensitivity and high resolution. So this kind of setup would have advantages where things like it wouldn't require lots of extra amplification of the signal. Alternatively, we can go to higher carrier concentrations, and this results in a lower temperature coefficient, lower linearity error, and a wide usable field range at these low temperatures. So that's something that we can then take all the way through into our end devices and end up with kind of tailor-made devices for these various conditions. So this is something that I've just highlighted here with our cryo-rated products. So you can see they have different sensitivities based on this control of carrier concentration, and then these different field and temperature ratings depending on the application. So to kind of demonstrate why we need to control these things at cryogenic temperatures, this is just some data using 3 different sensitivities. So we've called them high, medium, and low sensitivity devices. However, you can see that the sensitivity of the low sensitivity device is still 250 volts per amp Tesla, which relative to these ones, it's low, but actually that's quite sensitive. So these 3 devices were tested over a wide field range. And you can see that with the high sensitivity, we see a high response. And we reach at about 3 Tesla, we're reaching this, the first of those quantum resistance plateaus that I showed earlier. Whereas by controlling the carrier concentration, we can have a range of different responses. And by bringing it down to the level of this red one at the bottom here, we can see that the response carries on in a linear fashion. And so we predicted that it would, in fact, carry on. It's quite far from this standard, so would carry on quite fast. So we did actually do some more testing on this at HFML. And over a range of 16 Tesla, it's still looking very linear. So pushing it a bit further up to 30 Tesla, we're still seeing a very nice linear response over most of that range. And in fact, it's still quite far from this first quantum plateau. So could potentially carry on to around 46 Tesla. And so just to put these kind of high fields in a bit of context, 1 Tesla is enough to pick up a car. 20 Tesla around here is roughly in the region of most kind of research-based magnets. For the really high ones, for example, the highest sort of sustained magnetic field would be around 45 Tesla. So really going into the extremes of what it could be used for, and showing good performance over that range. So how does that compare to a conventional 2 deg sensor? So again, this is just some testing against a commercially available sensor, and we can see that at low fields, as it's swept along here, we can see quite a similar response between the two, between the Paragraf graphene and the commercially available sensor. Whereas around 15-16 Tesla, we see a drop off in the 2 deg sensor, whereas still that same linear response that we showed on the plot before. And then at those really high fields, we're seeing a much bigger drop off in the properties of the commercially available sensor, and we're seeing this kind of non-unique Hall voltage results here. So this is just a nice comparison over the full 30 Tesla range that was done at HFML. And the power dissipation actually at this highest field is only 10 picowatts, so very, very low power. So taking the temperature down a bit further and a bit more extreme, using the highest sensitivity from that range that was shown there. So this is some data that was taken at 20 millikelvin. And again, we can see these plateaus start to come into play, but we see a usable linear response between around -6 and 6 Tesla. So this is a really exciting result. This is the only Hall sensor demonstrated at these kind of ultra low temperatures. And within this range, you can see it's a really clear linear response. So this is a really interesting result here. However, it's not just the cryogenic temperatures. This sensor does operate over a wide temperature range. So we can see here going all the way from extremely low temperatures to ambient temperatures. So this means that with one sensor, you could have a continuous and accurate measurement through the entire range. And the temperature coefficient is also quite easy to calibrate for because it's small and repeatable. So quite easy to have a handle on the behavior there. So one application at ambient temperatures that I'll just touch on briefly would be for battery mapping. So this is the Hall sensor here attached to the outside of a battery, where it uses the magnetic field generated by currents in the battery to sense the current flow. And this can be done for currents over quite a wide range from milliamps to tens of kiloamps. And it can also measure the direction as well as magnitude, which is very useful. And it's immune to in-plane stray fields and has a very fast response. So really suitable for this kind of application. And this could be helpful at many stages of the battery's life, from the R&D stage to in-service, like battery health checking during performance, right through to the end of the battery's life. So looking at screening for suitability for recycling or reuse of batteries. So a lot of different uses here. And this data just kind of shows the kind of response that we see. So we can see that during the discharge at a certain current, that's being measured and picked up by the Hall sensor with a very kind of fast response when that is switched off, and a very clear kind of response between the different currents as well. So a very accurate and very fast measurement of the current flow. So I won't go into this too much more now, but there is another webinar that's available online that my colleague Hugh gave recently for the Graphene Council as well. So if this is of interest, then do have a listen to Hugh's webinar as well. So I'll now move on instead to a high temperature, which is something that is a research and development in progress for us at the moment. So this is something that we really want to kind of push into, having got that range of the low temperatures through to ambient temperatures. We want to extend that into high temperatures as well. And this is, again, another area where graphene can have key advantages over conventional materials. And this rough sketch just kind of illustrates the advantage of graphene with its more linear resistivity behavior over a range of temperatures. We're not seeing any kind of sudden and sharp changes, so it's much easier to kind of have a handle on over a range of temperatures. So the temperature that's our aim currently is needs to be a minimum of 125 degrees Celsius. And this is because of automotive applications having this requirement. So again, a range of areas within that this could be used for. So the current sensing, also positional sensing, motor control, and all of these things would have a certain high temperature requirement. So this is something that we're researching and developing in a variety of ways, from electronics control to trying to make sure that the whole assembly can still perform, because graphene is still very much able to perform at these temperatures, and it's the interfaces and the interactions and the rest of the assembly that we're optimizing in a variety of different ways to make these high temperature capable devices. So joining onto that a little bit with the angular resolution results. So again, this is something that is performing really well at ambient temperatures. So this plot here just shows an example test of an R&D sensor using angle measurements over roughly 60 degrees to minus 60 degrees. And we can see that the peak error within that range is less than 0.1 of a degree. So this is a really promising result for a kind of bare device, if you like, because it's quite competitive with conventional sensors once they've had corrections and kind of post-processing to the data. So that's a really promising result. Something that feeds into this as well is the lack of planar Hall effect in the graphene. So because we're using monolayer graphene as our active material, we don't have a kind of a depth to the device, so we don't see any kind of spurious signals through the thickness of the device. So that's a big advantage for graphene in this. So it would be good to target this kind of high performance at higher and higher temperatures and at smaller and smaller size. So this is very much something that's in progress. So looking at, for example, this kind of size reduction, this is a kind of standard package, and then moving down to a much smaller one where the active area goes from sort of on the millimeter scale to the tens of micron scale. So opens up a range of improvements there. So I'll just touch briefly on another extreme environment. So radiation exposure is something that we have done some testing on at NPL, again using R&D sample devices and exposing those to a very high neutron dose. So using 679 millisieverts. So just as a kind of comparison, that's kind of like 6,000 or 7,000 chest X-rays in that dose. So quite a high dose, and the sensors were then tested before and afterwards, and showed a minimal difference in their response, so around 0.2%, which is a really promising result and just helps to kind of show the general robustness of the material and of the device as well. So I'll just summarize by going over again those capabilities of the technology currently. So with our products that are capable for the cryogenic temperatures through to ambient and the high field applications as well. And then our main kind of R&D progress at the moment is with our high temperature capabilities. So this is for our Hall effect sensor, and there are a lot of other things going on at Paragraf as well. So I've got lots of colleagues doing very exciting things with biosensing using graphene, so for things like diagnostics, and then solid state technologies as well. So opening up the doors to a range of different structures and devices. So lots of exciting things going on, lots of exciting things in the future. So thank you very much.
Well, thank you, Rosie. Really appreciate that. That was a lot of information in a short period of time, and really fascinating. I have a few questions of my own, and we have questions from the audience. So I'll start with one of my own questions first, and then we'll go to the audience and ask some questions that they have about your presentation. With the shift to the electrification of transportation and EVs, we have different motor control. You have obviously the battery packs. There's a lot more going on there. Do you see the shift to the electric vehicles in transportation driving demand for this kind of a sensor? And if so, where and how?
Yeah, I think that's a really good point, because obviously we've kind of covered some of the applications in the kind of conventional automotive industry, but with the shift to more electric vehicles, obviously things like this battery mapping and things like that become much more relevant. And obviously with different types of motors and different technologies in the vehicles as well, there's a whole range of different opportunities for the sensors to be used and for the improvements to be implemented.
So I am not a scientist, as anybody who knows me knows. So I might need some help from you on some of the questions here, because these are some of them can be quite technical. So one of the questions is, what are the mobility average and D over G Raman averages? So I guess that's the Raman scans, the D to the G signal, giving pretty pure graphene. I imagine it tests as such.
Yeah, so in terms of the electrical properties themselves, of the kind of raw as grown graphene, that's pretty much all rolled up in our key intellectual property. So we more tend to kind of focus on the end properties and the end performance of the devices once they're kind of taken through that whole process.
One of the questions, and I'm not going to take these in any particular order, but how do you measure the magnetic fields used to test the sensor to know the field strength and the field uniformity over the area?
I'm not sure I caught all of that question. Can you repeat that one?
Yeah, I think the essence of the question is, when you're stating the strength of the magnetic fields used in the testing, how do you test the strength of the magnetic field? I think that's the question.
Okay, yeah. So you'd have to calibrate everything, and the sensor would be kind of pre-calibrated with other equipment. So
yeah. There's another question here, which I think is answered pretty much in your presentation, and I'm going to add a little twist on it. So one of the questions is, what are the benefits of your sensor over current MR/Hall position angle measuring devices in automotive? And I guess the other question I have that's kind of included with that, or on top of that, you have these sensors which obviously can perform in environments in which conventional Hall effect sensors cannot. But is there an advantage in the normal use within that conventional range that also make these competitive? So those are two different questions. This one's talking specifically about the angle measuring devices, but how does this device compare, not just in the extreme environment, but in conventional use at the moment?
Yeah, so I think that's a really good question. I think the electrical properties of the graphene and things like the 2D nature of the material, and the fact that we're just kind of using a monolayer, give it a lot of advantages over conventional materials. So things like the planar Hall effect that I mentioned, give it a lot of advantages just as a kind of a bare raw material, and then it doesn't then need a lot of things like extra kind of electronics and amplification and things like that, that would need to be added into other materials. And I think the angular sensing is a good example of that, like I showed with that plot. It was kind of getting similar numbers to conventional materials that would require some processing and some correction.
Excellent. I think you also made the fact that for some testing environments, you might need multiple sensors to get the right range and the variance there, whereas with your sensors, you can use a continuous range. And so then you eliminate, having more than one sensor for that application, if I understood correctly.
Yeah, so having one sensor that can do this range of things and operate in this range of conditions gives a huge advantage. And also having a sensor that can do all of that in situ, in service, rather than needing to wait for conditions to be changed to make the measurement, which is not a true representation.
Right. I would also assume that the robustness of this sensor, because it can operate in this really wide range of environments in harsh conditions, has a better survivability and longevity to it.
Yep, that's the aim. Yeah.
Another question I would have is on the form factor. You mentioned it gets down to, I believe you said tens of microns
Mm-hmm.
in sensing area. And another point that wasn't highlighted too much, but it's certainly there, is its lower power consumption, right? To perform. Do you guys see particular applications where the form factor is a key competitive advantage for you?
Yeah, I think anything kind of where small sensors are required. So anything with maybe a weight constraint, such as space-based applications, or in general, automotive and aerospace, any kind of reduction in size and weight is always desirable. And also for things like spatial resolution, a small size enables greater resolution.
Excellent. A couple more questions from the audience. One is, what is this? If you can speak to this, you might not be able to if it's confidential. But what is the substrate material in radiation hard sensors?
Yeah, so again, that's something that's all kind of tied up in how we manufacture our end structure. So can't go into that too much.
Understandable. Another question is, how do you maintain the homogeneity of the graphene area do you use a resist mask? Again, that's probably another trade secret or confidential question, but we know from our experience over the past years working with graphene, to get a really uniform single crystal defect free is not easy. But is there anything related to that you can speak to?
So again, yeah, that's kind of our key, the key kind of USP of our graphene is that fabrication process that enables that uniformity and that quality over a whole wafer that we can then make into the devices.
Understood. They need to buy your sensors. That's what they need to do.
Have it,
So
yeah, come and have a chat to us.
there you go.
Send some inquiries. We'd love to have a chat.
There you go. Another question here: is there any idea to build a 2D/3D magnetic sensor?
Yep. So that's definitely something that is opened up by this, and particularly by things like the small size of the device. There's scope for all sorts of different sensing assemblies.
Excellent. Okay. So I guess there is another question. I know you mentioned the size, but there's a question specifically about the size. So what is the smallest form factor you're down to now?
So the active area of the smaller size device is around is in the low tens of microns. I would say currently.
Okay. Another question I have, and I'm going to come back to the audience. By the way, it's great that everybody is so interested and we have so many questions. So, feel free to keep them coming, and we'll stay on here as long as we have questions to answer. You mentioned, with harsh environments, one of the things that comes to mind is space, outer space, satellites, miniaturization. Obviously, radiation's a concern in that. How much of the work are you doing? You don't have to say specifically, but are space applications, is that a high area of interest? And I would also assume that there are some defense industry related applications here.
Yeah, so obviously that's a consideration, and we have to kind of consider things like that with all the ranges of markets that we're looking at. So at the moment, the key one for us is the kind of automotive aerospace, and looking to push to those higher temperatures. But at the same time, it's good to know from our testing the capabilities that it has for other applications like the space-based ones as well.
I was also fascinated when you mentioned that you've tested under high fields of radiation. And of course, with the push to renewable energy, nuclear power is enjoying a bit of a renaissance, and I think we are going to see more nuclear power plants built over the next years. What kind of applications do you see in a nuclear power generation field, or are there other more medical related? Because medical, obviously, you have some imaging technologies that use radiation. Where do you see these high radioactive environment applications for this type of sensor?
Yeah, so I think that there'd be a huge range of applications in, like you say, in all those fields, in the nuclear materials and the medical, and I think it's not something that we have done too much on at the moment, but there's definitely a huge range of opportunities there for the sensing.
Excellent. There's a couple more questions. One of them is simply asking, are there data sheets or some kind of product descriptive sheets that are available for this, or do people need to contact you to get that kind of information?
Absolutely, yeah. If people would like to visit the website, which is paragraf.com, then there's plenty of information available on there, and you can absolutely get in touch with us and start some interesting conversations.
Excellent. Let me just go through a couple more questions. And by the way, Rosie, if you're able to read some of the questions that you would like to address, feel free to just pick one. One of them is a maximum operating temperature that these sensors can perform at. And I guess that would be the question, right? So what high temperature applications? But what do you think the upper limit is for you guys on the temperature range?
So in terms of the graphene as a material itself, that obviously has an extremely high range of temperatures at which it can perform. So in terms of what's kind of limiting the maximum temperature, it would probably be the kind of the rest of the assembly. So at the moment we're looking at 125 degrees, but for a lot of automotive applications, there are some kind of uses that would require higher, so 180 over 200. So it should be just a case of kind of ensuring that the other materials and that the whole assembly can perform at those temperatures, because the material itself should, in theory, work well.
Yeah, I was going to say my understanding from the temperatures at which the carbon sublimates, or the upper end of the range, it's probably the substrate and the other components that would fail before the graphene fails from temperature. Is that a fair statement?
Yeah, that's true.
There's a question here. Any test regarding magnetic rails? And I'm not sure if magnetic rails is a common term that everybody understands, but there is some defense applications of using magnetic rails to launch projectiles. And I am assuming that's what it could be, or the other could be levitation for trains. So I'm not sure. It's either defense projectiles at high speed using magnetic rails or railgun, or using it for transportation and elevation. So either
two very different and very interesting applications.
Yes.
Not things that we have kind of tested in situ specifically, but again, obviously there are lots of different uses and lots of different opportunities.
There's a question. Obviously, I'm surprised it took this long on cost.
I could tell you were looking at that one.
Yeah, yeah. So like all applications, I'm not going to ask you to discuss price on this, because that's not really what we do on these. We're more looking at the technical side. But obviously, with almost all applications related to graphene, you have to look at the value add for the application given. It's also usually typically quite volume driven. But the fact is that Paragraf is producing these materials for sale now. So this isn't just a theoretical R&D product. This is actually being used, correct?
Yeah, that's right. So we have a growing commercial arm to the business. So it's kind of their job to look at things like the pricing, and that's based on things like volume and how the device compares in performance to things that are available, or in some cases where there's nothing really that performs in the same way. And so that's kind of the things that they have to consider, and that's something that they'd be more than happy to talk about if there are any inquiries about buying the sensors.
Excellent. There's a more technical question. I think it's been addressed in the presentation, but let's put this forward. It said, can you speak to the low magnetic field sensitivity and spatial resolution and noise immunity, which I think you referred to. Part of that was the nature of the monolayer graphene itself being immune to some of these interference. But can you speak to that question?
Yeah, so the 2D nature of it does mean that we kind of negate a lot of the kind of erroneous signals that we would see in other materials that have a kind of a depth to them. And there's also a range of, I think I touched on briefly on the kind of electronics improvements that can be made as well. So things like spinning current and other kind of error cancelling things that can be done. So everything with the device is kind of very easily understood and calibrated.
Excellent. Excellent. So I'm going to ask just one more question, and I think we're going to wrap it up here. I know we still have a few maybe unanswered questions, but I would encourage people to reach out to you directly if they would like more information. And the fact you've been working with this for quite a while and obviously quite knowledgeable about it, I think they'll get great answers from you. The question was just on which of the applications do you think, because I know that you already have these sensors deployed, but where do you see the biggest commercial pull for your products? Which applications do you think are going to be the most significant commercially in the next 6 to 12 months?
Yeah, so excitingly, we have kind of made a lot of sales, and we have a lot of kind of interesting collaborations as well. So from the kind of the more research-based to the more commercial, and I think for us, like I mentioned at the end there with the kind of R&D progress, I think the automotive market is going to be a huge one for us, and so that's something that we're very keen to kind of tailor devices towards, because that could be very kind of high volumes.
Excellent. Well, as we discussed, the shift to the electric vehicles, we know, is driving all sorts of new engineering challenges for companies because of the drive structure and all sorts of different requirements from the battery packs, from the motors, but then all of the sensing devices that they have within the vehicles. And I think it opens up opportunities for people to look at the systems from front to back. And so looking at new applications for your product should be in that mix. On behalf of the Graphene Council, and again, if you folks are anybody who's not familiar with the Graphene Council, we are a neutral global trade and professional body representing the industry. And one of the things we do is to try to educate people about how graphene can and is being used. Today's webinar is an example of that, and we're very proud to have Paragraf as one of our member companies. And Rosie, I want to thank you personally for your time putting the presentation together and sharing the knowledge that you have about this really interesting frontier development of graphene in these Hall Effect sensors. So thank you for that.
Thank you very much. It's been a great opportunity.
All right, my pleasure. And with that, everybody stay safe, and we'll keep in touch. Take care. Have a great day.